Aero Engineering Thermodynamics. Coefficient of performance. The efficiency of a refrigerator is expressed in terms of the coefficient of performance COP denoted by COPR. The objective of a refrigerator is to remove heat QL from the refrigerated space. The COP of refrigerator is the ratio of desired output to the required input. The conservation of energy principle for a cyclic device requires that COP equals QL/QH. QL. The value of copper can be greater than unity. That is, the amount of heat removed from the refrigerated space can be greater than the amount of work input. In contrast to the thermal efficiency, which can never be greater than 1. The objective of a refrigerator is to remove QL from the cooled space. Heat pumps. Another device that transfers heat from a low-temperature medium to a high-temperature one is the heat pump, shown schematically in figure. Refrigerators and heat pumps operate on the same cycle but differ in their objectives. The objective of a refrigerator is to maintain the refrigerated space at a low temperature by removing heat from it. The objective of a heat pump is to supply heat QH into the warmer space. The objective of a heat pump, however, is to maintain a heated space at a high temperature. This is accomplished by absorbing heat from a low-temperature source, such as well water or cold outside air in winter, and supplying this heat to the high-temperature medium such as a house. The work supplied to a heat pump is used to extract energy from the cold outdoors and carry it into the warm indoors. The measure of performance of a heat pump is also expressed in terms of the coefficient of performance COPHP, defined as COP of the heat pump is equal to the ratio of desired output to required input, which can also be expressed as. This relation implies that the coefficient of performance of a heat pump is always greater than unity since copper is a positive quantity. That is, the heat pump will function, at worst, as a resistance heater, supplying as much energy to the house as it consumes. Most existing heat pumps use the cold outside air as the heat source in winter, and they are referred to as air source heat pumps. The COP of such heat pumps is about 3.0 at design conditions. The second law of thermodynamics, Clore-Cu statement. The Clore-Cu statement is related to refrigerators or heat pumps. The Clore-Cu statement is expressed as follows. It is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature body. The Clore-Cu statement does not imply that a cyclic device that transfers heat from a cold medium to a warmer one is impossible to construct. It simply states that a refrigerator cannot operate unless its compressor is driven by an external power source, such as an electric motor. The refrigerator that violates the Clore-Cu statement of the second law. Equivalents of the two statements. The Kelvin-Planck and the Clore-Cu statements are equivalent in their consequences, and either statement can be used as the expression of the second law of thermodynamics. Any device that violates the Kelvin-Planck statement also violates the Clore-Cu statement, and vice versa. A device that violates the second law of thermodynamics is called a perpetual motion machine of the second kind. PM2. Two familiar reversible processes Reversible and irreversible processes. A reversible process is defined as a process that can be reversed without leaving any trace on the surroundings. Both the system and the surroundings are returned to their initial states at the end of the reverse process. This is possible only if the net heat and net work exchange between the system and the surroundings is zero for the combined original and reverse process. Processes that are not reversible are called irreversible processes. Irreversibilities. The factors that cause a process to be irreversible are called irreversibilities. They include friction, unrestrained expansion, mixing of two fluids, heat transfer across a finite temperature difference, electric resistance, inelastic deformation of solids, and chemical reactions. The presence of any of these effects renders a process irreversible. Internally and externally reversible processes. A process is called internally reversible if no irreversibilities occur within the boundaries of the system during the process. During an internally reversible process, the system proceeds through a series of equilibrium states, and when the process is reversed, the system passes through exactly the same equilibrium states while returning to its initial state. The quasi-equilibrium process is an example of an internally reversible process. Internally and externally reversible processes. A process is called externally reversible if no irreversibilities occur outside the system's boundaries during the process. Heat transfer between a reservoir and a system is an externally reversible process if the outer surface of the system is at the temperature of the reservoir. A process is called totally reversible, or simply reversible, if it involves no reversibilities within the system or its surroundings. Fig. A totally reversible process involves no heat transfer through a finite temperature difference, no non-quasi-equilibrium changes, and no friction or other dissipative effects. The reversible process involves no internal and external irreversibilities. The Carnot cycle. Probably the best known reversible cycle is the Carnot cycle, first proposed in 1824 by French engineer Sadi Carnot. The theoretical heat engine that operates on the Carnot cycle is called the Carnot heat engine. The Carnot cycle is composed of four reversible processes, two isothermal and two adiabatic, and it can be executed either in a closed or a steady flow system. Consider a closed system that consists of a gas contained in an adiabatic piston cylinder device, as shown in Fig. The insulation of the cylinder head is such that it may be removed to bring the cylinder into contact with reservoirs to provide heat transfer. The four reversible processes that make up the Carnot cycle are as follows. Reversible isothermal expansion process 1 to 2, Th constant. Initially state 1. The temperature of the gas is Th and the cylinder head is in close contact with the source at temperature Th. The gas is allowed to expand slowly, doing work on the surroundings. As the gas expands, the temperature of the gas tends to decrease. But as soon as the temperature drops by an infinitesimal amount dt, some heat is transferred from the reservoir into the gas, raising the gas temperature to Th. Thus, the gas temperature is kept constant at Th. Since the temperature difference between the gas and the reservoir never exceeds a differential amount dt, this is a reversible heat transfer process. It continues until the piston reaches position 2. The amount of total heat transferred to the gas during this process is Qh. Reversible adiabatic expansion process 2 to 3, temperature drops from TH to TL. At state 2, the reservoir that was in contact with the cylinder head is removed and replaced by insulation so that the system becomes adiabatic. The gas continues to expand slowly, doing work on the surroundings until its temperature drops from TH to TL state 3. The piston is assumed to be frictionless and the process to be quasi-equilibrium, so the process is reversible as well as adiabatic. Reversible isothermal compression process 3 to 4, TL constant. At state 3, the insulation at the cylinder head is removed, and the cylinder is brought into contact with the sink at temperature EL. Now the piston is pushed inward by an external force, doing work on the gas. As the gas is compressed, its temperature tends to rise. But as soon as it rises by an infinitesimal amount dt, heat is transferred from the gas to the sink, causing the gas temperature to drop to TL. Thus, the gas temperature remains constant at TL. Since the temperature difference between the gas and the sink never exceeds a differential amount dt, this is a reversible heat transfer process. It continues until the piston reaches state 4. The amount of heat rejected from the gas during this process is QL. Reversible adiabatic compression process 4 to 1, temperature rises from TL to TH. State 4 is such that when the low temperature reservoir is removed, the insulation is put back on the cylinder head, and the gas is compressed in a reversible manner. The gas returns to its initial state, state 1. The temperature rises from TL to TH during this reversible adiabatic compression process, which completes the cycle. On a PV diagram, the area under the process curve represents the boundary word for quasi-equilibrium internal irreversible processes. We see that the area under curve 1, 2, 3 is the work done by the gas during the expansion part of the cycle, and the area under curve 3, 4, 1 is the work done on the gas during the compression part of the cycle. The area enclosed by the path of the cycle area 1, 2, 3, 4, 1 is the difference between these two and represents the net work done during the cycle. The Carnot heat engine cycle just described is a total irreversible cycle. Therefore, all the processes that comprise it can be reversed, in which case it becomes the Carnot refrigeration cycle. This time, the cycle remains exactly the same, except that the directions of any heat and work interactions are reversed. Heat in the amount of QL is absorbed from the low temperature reservoir. Heat in the amount of QH is rejected to a high temperature reservoir, and a work input of W and ET is required to accomplish all this. The PV diagram of the reversed Carnot cycle is the same as the one given for the Carnot cycle, except that the directions of the processes are reversed, as shown in Fig.